Assalamualaikum. Today I will present my final project with title Rare Earth Doping in Yttrium Barium Copper Oxide Superconductor. Introduction. First, background of study. The YBCO superconductor is currently being researched due to its ease of preparation, dependability, and low cost. Many researchers are now revealing superconductor in many types of material that can enhance the critical temperature superconductor, such as the addition of 50% of silver to YBCO superconductor, which has metallic properties. For example, doping high temperature superconductor with AU nanoparticles generates the additional flux spinning energy and enhancing the critical current density. Second problem statement. The impacts of material manipulation on high temperature superconductors with Tc above 77 Kelvin can be examined by doping impurities into the crystal structure. Many efforts are now being made to improve the electrical performances of this system using YBCO coated conductors doped with rare earth elements, which are known as the critical current density and critical temperature. Many studies have been undertaken to observe TC and JC performances due to varying percentage of impurity doping such as plumbum, argentum, calcium, antimony, and samarium in various YBCO superconductor sites. As a result, using rare earth to add nanoparticles and chemical doping to superconductor materials, as well as monitoring their location, is an effective way to improve superconducting capabilities. Next, research objective. The objective of this research review are: first, investigate the preparation method of YBCO superconductor. Second, study the structure of YBCO superconductor and its physical properties. Third, discuss the rare earth doping in YBCO superconductor. Significance of the study. This review of research will present several methods for preparing YBCO superconductor. Aside from that, this research review describes the structure of YBCO superconductor and its physical properties, as well as the effects of rare earth element doping on the superconducting properties of YBCO. The analysis that is presented in this study will convey valuable information for future research that will explore the rare earth barium copper oxides, especially YBCO. Furthermore, the overview presented in this study will encourage a new approach that will be useful for future discussion of rare earth YBCO and may lead to a more in-depth analysis of it. The structure and properties of YBCO superconductor. Y123, Y124, and Y247 are the three known members of the Y-based homologous family of superconductors. The most stable of these three is Y124, which has a constant oxygen content in the unit cell. However, the zero-resistant critical temperature of Y124 is 80 degrees Celsius, which is quite close to the boiling point of liquid nitrogen, which is limiting its usage for prospective application. The Y123 superconductor has a Tc value exceeding 90 Kelvin. However, it is thermodynamically brittle and begins to lose oxygen at temperature above 300 degrees Celsius. Because of the structure, Y247 is made up of alternating layers of Y123 and Y124. It should be more stable. Depending on the oxygen level, the Y247 displays a superconducting transition with Tc varying from 30 to 95 Kelvin. The Y123 has two CuO2 planes and one CuO chain, whereas the Y124 has one CuO double chain and the Y247 has one CuO2 plane and one CuO chain as well as the one double chain. The number of CuO2 plane and the CuO chain have a significant impact on the transition temperature Tc of the YBCO superconductor. First, doping YBCO superconductor with Ce3+. Figure 2 shows the Ce doped and undoped YBCO SRD patterns. According to the SRD patterns, all of the doped samples were polycrystalline with orthorhombic PMMM symmetry. Also, according to the SRD pattern, the dominant polycrystalline phase was found to be the Y123 phase. Figure 3 shows the temperature dependence of Ca-doped YBCO resistivity. The critical transition temperature decreased from 85.91 K for the undoped YBCO sample to 79.5K and 80K for the doped sample with the rising CE and GD contents from x equal to 0 to x equal to 0.1 respectively, as shown in figure 3. Figure 4 shows the CE doped YBCO sample SEM image in ABC at x equal to 0.01, 0.05 and 0.1. After increasing the CE contents, a dense surface is obtained with a systematic change of the size and the shape of the grains, where the grain boundaries have practically disappeared, as shown in figure 4A until C. Second, doping YBCO superconductor with GD3+. Figure 5 shows the GD doped and undoped YBCO sample as RD patterns. As a result, the intensity of the associated Y123 peaks decrease as the GD dopant levels are increased further, while the peak intensity of the minor phase increased significantly with GD addition. Figure 6 shows the temperature dependence of GD doped YBCO resistivity. There has been an example where the attained critical transition temperature of 88K is greater than the undoped sample when integrating using x equal to 0.01 of GD content. Figure 7 shows the GD doped YBCO sample SAM image in DEF at x equal to 0.01, 0.05 and 0.1. In particular, better texturing, connectivity between grains, and regular crystal plane alignment were achieved, as well as uniform surface morphology are obtained for GD doped YBCO sample with x equal to 0.01. Third, doping YBCO superconductor with dy3+. Figure 8 shows the SRD patterns for the conventional solid state reaction. The samples feature a single phase of orthorhombic Y123 structure, as can be observed from the SRD data. The samples carefully contain any impurities, that is, parameters don't change all that much. The orthorhombic strength, on the other hand, reduces for the sample dy1 and dy08, in which A and B are the lattice parameters of the samples. Table 1 shows the dimension, lattice parameters, unit cell volume, and orthorhombicity for all the samples. Table 1 shows that, with the exception of dy04 and dy06, the lattice characteristic of the dy doped YBCO sample rise with the dopant. Figure 9 shows the plot of normalized versus temperature for the investigated samples of f equal to 20 Hz and HAC equal to 1. At particular doping rates x equal to 0.2, 0.4 and 0.6, dy substitution enhance the critical temperature Tc. Lastly, recommendation and suggestion. Aside from gadolinium, cerium and dysprosium, there are other rare earth elements that could be doped into YBCO superconductor, such as chromium, which is also classified as traveler rare earth ion. In conclusion, cerium doped YBCO superconductor samples was produced using the conventional solid state reaction. GD doped YBCO was also synthesized by using the conventional solid state reaction. The critical transition temperature decreased from 85.91 K for the undoped sample YBCO sample to 79.5 K and 80 K for the doped sample, with rising the CE and GD contents from x equal to 0 to x equal to 0.1 respectively. However, there has been an example where the attained critical transition temperature of 88K is greater than the undoped sample when integrating using x equal to 0.01 of GD content. Furthermore, dy doped YBCO were also generated using the solid state reaction. The dimagnetic transition temperature for the sample where x equal to 0, 0.2, 0.4, 0.6, 0.8 and 0.1 are determined to be 91.3, 92.2, 92.4, 91.4 and 62K respectively. Finally, this slide shows the references that I have been used for this presentation. Thank you for watching this video presentation.